Hello, sleepy genius. The day has asked so much of you, and now the night offers something in return. Rest, stillness, and a question so vast it could unfold across eternity. Let your breathing slow, let your thoughts drift. Tonight, we journey not through space, but through time itself, far beyond what any mind has dared to imagine. From new species evolving to replace humans as Earth's dominant intelligence, to entire continents colliding and reshaping the planet, to the very atoms that once formed your body scattering across galaxies yet to be born. And you're going to witness every single moment of it. Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please, share your thoughts below. Now, let's begin. In 10,000 years, every language spoken today will be unrecognizable. Imagine a child in the distant future trying to read Shakespeare or listen to a recording of someone speaking English, and finding it as alien as ancient Sumerian is to us now. Linguistic studies by researchers at the Max Planck Institute in 2007 show that languages evolve so rapidly that mutual intelligibility is lost in roughly 1,000 years. In 10,000 years, the Great Pyramid will still stand, but no one will be able to read the inscriptions on buildings from our era without extensive training. The digital records we create today, stored on servers and hard drives, will have degraded into meaninglessness unless continuously maintained. To think that every word we speak, every song we sing, is destined to become an archaeological puzzle for minds we cannot imagine. In 20,000 years, the Chernobyl exclusion zone will finally be safe for permanent human habitation. Picture forests grown thick over the reactor, animals thriving in what was once a dead zone, the radiation slowly decaying into harmless elements. Plutonium-239, one of the most dangerous isotopes released in the disaster, has a half-life of 24,000 years. Studies by radiation ecologists at the University of Georgia in 2016 show that while some areas recovered faster than expected, the most contaminated sites will remain hazardous for millennia. By 20,000 years, the last traces of our nuclear age will have faded from this place, and new soil will have buried the scars. This reminds us that some wounds we inflict on the earth heal only on timescales that dwarf civilizations. In 50,000 years, Niagara Falls will have eroded away to nothing. Imagine standing where the thundering cascade once stood, finding only a gentle river flowing through a wide valley. The falls are retreating upstream at a rate of about 1 meter per year, carving through soft sedimentary rock. Geological surveys by the US Geological Survey show that in 50,000 years, the falls will have moved all the way back to Lake Erie, effectively eliminating the drop. One of the natural wonders millions visit each year will vanish, not through catastrophe, but through the patient work of water on stone. It is humbling to realize that even the landmarks we consider permanent are merely temporary sculptures being slowly erased. In 100,000 years, humanity will have evolved into a visibly different species. Picture humans with slightly different skull shapes, altered proportions, features we would recognize but find subtly wrong. Studies in evolutionary biology by Stephen Stearns at Yale University in 2010 show that human evolution has not stopped. Despite modern medicine and technology, natural selection continues to act on traits like disease, resistance, reproductive timing, and even facial structure. In 100,000 years, the accumulation of small changes will create humans as distinct from us as we are from early Homo sapiens. Climate adaptation, genetic drift in isolated populations, and possibly intentional genetic modification will accelerate this transformation. To think that the face, looking back from the mirror, is not a finished product, but a single frame in an endless film of change. In 250,000 years, all current coral reefs will have died, and new ones will have grown in different oceans. Imagine the Great Barrier Reef dissolved into sand, its colors faded, while near the poles, where waters have warmed, new reefs bloom in places that were once too cold. Research published in 2020 by marine biologists at the University of Queensland shows that coral reefs can recover from mass extinctions, but it takes 100,000 to 200,000 years for full ecosystem recovery. As oceans warm and chemistry changes, reefs will migrate toward cooler waters, and entirely new coral species will evolve to fill niches. The reefs we fight to save today will be fossils, and the living reefs of that future will be populated by creatures that do not yet exist. In a sense, we are mourning not the death of reefs themselves, but the death of these particular reefs, this particular arrangement of life. In 500,000 years, a new species may have evolved to replace humans as Earth's dominant intelligence. Picture creatures descended from corvids, with their problem-solving abilities refined over 500,000 years, or perhaps octopuses that have developed social structures and language. Paleontological studies show that after major extinctions, it typically takes 500,000 to 5 million years for new dominant species to emerge. If humanity collapses or evolves beyond recognition, the cognitive niche we occupied will not remain empty. Research by neurobiologist Laurie Marino in 2015 suggests that several species, including dolphins, elephants, and certain birds, possess the neural foundations for complex intelligence. Given enough time and evolutionary pressure, any of these lineages could produce technological civilizations. This reminds us that intelligence may not be unique to our branch of the tree of life, but rather an inevitable outcome given the right conditions and enough time. In 1 million years, the Yellowstone supervolcano will have erupted at least once. Imagine a column of ash rising 40 kilometers into the stratosphere, blotting out the sun across North America. Temperatures plummeting globally as particles reflect sunlight back into space. Yellowstone erupts roughly every 600,000 to 800,000 years, and the last eruption was 640,000 years ago. Studies by the U.S. Geological Survey show that when it does erupt, it will eject more than 1,000 cubic kilometers of rock and ash, creating a volcanic winter that could last years. Crops will fail across continents, and any human population will face catastrophic famine. But life will persist in pockets, and within 10,000 years, ecosystems will begin to recover. To think that beneath the peaceful geysers and hot springs lies a force capable of reshaping civilizations, waiting with geological patience. In 2 million years, every human-made structure will have crumbled to dust. Picture cities reclaimed by forests, steel towers collapsed into rust, concrete highways fractured into gravel, scattered among the trees. Even the Great Pyramids, built to last forever, will have eroded significantly. Research by geologists at the University of Leicester in 2013 shows that without maintenance, most buildings collapse within 200 years, and even the most durable structures succumb to erosion, root growth, and chemical weathering within thousands of years. In 2 million years, only faint chemical traces in the soil and perhaps some ceramic fragments will hint that a technological civilization once existed. The geological layer marking our time will be a thin band of plastics, concrete, and radioactive isotopes that future geologists might puzzle over. It is humbling to imagine that everything we build, every monument to our permanence, is as temporary as a sandcastle before the tide. In 5 million years, the Antarctic ice sheet may have completely melted. Imagine a continent green with tundra and boreal forests, rivers flowing through valleys that were carved by glaciers that no longer exist, animals migrating across land bridges that emerged from beneath the ice. Climate models developed by researchers at the University of Massachusetts in 2016 show that if carbon dioxide levels remain elevated, Antarctica could become ice-free, as it was during the Eocene epoch 50 million years ago. Sea levels would rise by 60 meters, drowning every coastal city that exists today. The reshaping of ocean currents would alter global weather patterns, creating climates unlike anything in human memory. To think that the frozen continent, symbol of Earth's last wilderness, could transform into something entirely different, inhabited by species that evolved in the warmth. In 10 million years, a new intelligent species descended from rats may inherit the Earth. Picture creatures the size of dogs, with elongated fingers for tool manipulation, living in complex underground cities, their ancestors having survived whatever catastrophe reduced humanity to memory. Rats are already highly adaptable, with rapid reproduction and omnivorous diets. Studies by evolutionary biologists Jan Zelicevic at the University of Leicester in 2009 suggest that rodents are prime candidates to fill ecological niches left vacant by extinctions. In 10 million years, these descendants might have evolved larger brains, social structures, and perhaps even rudimentary technology. They would find our fossils the way we find dinosaur bones, and wonder what strange giants once walked the world. In a sense, the meek really do inherit the earth, not through virtue, but through adaptability and patience. In 15 million years, the Mediterranean Sea will completely evaporate again. Imagine a vast salt desert stretching from Spain to Turkey, 5 kilometers below sea level, temperatures exceeding 60 degrees Celsius, salt pillars rising like ghostly monuments. This has happened before, during the Messinian salinity crisis 5.96 million years ago, when tectonic shifts closed the Strait of Gibraltar. Research published in 2009 by geologist Maria Roveri shows that the Mediterranean evaporated almost entirely within 1,000 years, leaving a hypersaline basin. When it refilled, it did so catastrophically, with water pouring in from the Atlantic at a rate 1,000 times the flow of the Amazon River. In 15 million years, this cycle may repeat, erasing every memory of the sea civilizations were built beside. This reminds us that even oceans are temporary, that geography itself is as fluid as the water that fills it. In 24 million years, the island of Mauritius will sink beneath the Indian Ocean. Picture the remnants of volcanic peaks disappearing beneath waves, coral reefs growing over the last traces of land, the entire island becoming a seamount like so many before it. Mauritius sits on oceanic crust that is slowly subsiding as it moves away from the volcanic hotspot that created it. Studies by geologists at the University of the Witwatersrand in 2013 discovered fragments of ancient continental crust beneath Mauritius, evidence of previous land masses that sank millions of years ago. In 24 million years, Mauritius will join them, and new volcanic islands will rise elsewhere along the hotspot track. The dodo, extinct for centuries, will be forgotten twice, its fossils submerged where no one can find them. To think that entire islands, complete with their unique species and evolutionary experiments, can vanish as if they never existed. In 50 million years, Africa will have collided with Europe, and Mount Kilimanjaro will be part of a mountain range taller than the Himalayas. Imagine standing on a peak in what was once the Sahara Desert, now thrust upward into the sky, glaciers clinging to slopes where sand dunes once rolled. The collision between the African and Eurasian plates is already building the Alps, but in 50 million years, the impact will create a continuous mountain chain from West Africa to Southeast Asia. Research by tectonics expert Du van Hinsbergen in 2014 shows that this range will rival the Tibetan Plateau in height, altering global weather patterns and creating new rain shadows and monsoon systems. Species will evolve in isolated mountain valleys, and new forms of life will emerge in the thin air of the peaks. In a sense, the Earth is always building new worlds on the ruins of old ones. In 80 million years, the descendants of dolphins may walk on land again. Picture creatures with elongated fins that have evolved into legs, returning to the shores their ancestors left 50 million years ago. Their intelligence now applied to terrestrial challenges. Evolution is not a one-way street. Several lineages have returned to environments their ancestors abandoned. Studies by paleontologist Hans Thuisen in 2009 show that whales evolved from land mammals, and there is no reason their descendants could not reverse the process if ocean conditions became unfavorable. In 80 million years, marine mammals facing overfished oceans or acidic waters might adapt to exploit coastal and terrestrial resources, eventually becoming fully terrestrial again. This reminds us that evolution is opportunistic, always exploring, always ready to revisit old solutions when circumstances change. In 100 million years, the Atlantic Ocean will begin to close. Imagine the seafloor buckling, new subduction zones forming. The ocean that Columbus crossed, shrinking year by year as the Americas drift back toward Europe and Africa. Research published in 2018 by geophysicist Joe Duarte at the University of Lisbon shows that old, cold oceanic crust in the Atlantic is becoming dense enough to sink, initiating subduction. In 100 million years, the Atlantic will be much narrower, and in 200 million years, it may close completely, bringing the continents together again. The cycle of supercontinent formation and breakup will continue, as it has for billions of years. To think that the ocean we consider permanent is merely a temporary gap between collisions, a breath between the planet's slow heartbeats. In 150 million years, a new supercontinent will be forming, and all borders, nations, and human geopolitical divisions will be meaningless. Picture land masses merging, the Pacific closing, or the Atlantic disappearing. Continents colliding to form a single massive landmass that future species will simply know as the land. Geologists have named potential future supercontinents Pangaea, Ultima, Novo-Pangaea, or Amasea, depending on which scenario proves correct. Research by Christopher Scotes at Northwestern University in 2003 modeled these possibilities. Using plate motion data, whichever configuration emerges, the climate will be extreme, with vast interior deserts and violent monsoons on the coasts. Any species alive then will be so different from us that calling them human would be like calling a dolphin a cow. In a sense, the Earth does not recognize our maps, our claims to territory, our carefully drawn lines. It simply moves according to forces too vast for borders to contain. In 200 million years, the descendants of squid may have developed complex civilizations beneath the sea. Imagine underwater cities built from coral and volcanic rock, bioluminescent communication networks spanning ocean basins, an entire technological society that never discovered fire but mastered chemistry, acoustics, and biological engineering. Cephalopods already possess sophisticated nervous systems, problem-solving abilities, and can change their skin patterns to communicate. Research by marine biologist Jennifer Mather in 2008 documents octopuses using tools, learning by observation, and exhibiting individual personalities. Given 200 million years without competition from humans, cephalopod intelligence could reach extraordinary heights. They would explore the ocean floor the way we explore space, and they might never know that dry land exists above them. This reminds us that intelligence might take forms completely alien to our experience. Civilizations built on principles we have never imagined. In 250 million years, all current mountain ranges will have eroded to plains. Imagine the Himalayas worn down to rolling hills, the Rockies flattened to gentle rises, the Alps reduced to memories in the rock record. Mountains rise quickly in geological terms, but erosion never stops. Studies by Kaylin Whipple at Arizona State University in 2009 show that even the tallest peaks erode at rates of millimeters per year, and without tectonic uplift to renew them, they disappear entirely within 100 to 300 million years. By 250 million years, Earth's surface will be relatively flat, save for the new mountains rising from the formation of the next supercontinent. The Appalachians, once as tall as the Himalayas, show us what awaits every mountain range: slow surrender to wind, rain, and time. To think that even the most permanent-seeming features of the landscape are temporary sculptures, always being carved away. In 300 million years, the new supercontinent will cause mass extinctions that dwarf anything in human history. Picture the interior of the landmass as an endless desert where temperatures regularly exceed 55 degrees Celsius, too hot for most vertebrates to survive. The coastlines will host the only habitable zones, creating intense competition for resources. Climate models by researchers at the University of Texas in 2018 showed that supercontinent formation typically triggers extinction events by eliminating shallow seas, disrupting ocean circulation, and creating extreme continental climates. The Permian extinction 252 million years ago, which killed 96% of marine species and 70% of terrestrial vertebrates, occurred during the formation of Pangaea. The next supercontinent will likely cause similar devastation, wiping out entire lineages and forcing evolution to start fresh in many niches. In a sense, the Earth periodically resets life's diversity, culling the old to make room for the new. In 500 million years, the Moon will be significantly farther from Earth. Imagine tides that barely rise, a month lasting 32 current days, the Moon appearing 15% smaller in the sky. The Moon is receding from Earth at 3.8 centimeters per year due to tidal interactions. Research by planetary scientist James Williams in 2016 shows that in 500 million years, the Moon will be far enough away that total solar eclipses will become impossible. The Moon will appear too small to cover the Sun completely. The slowing of Earth's rotation due to tidal friction means days will be 25 hours long. Any intelligent species alive then will experience a different rhythm of time, longer days and nights, weaker tides, and a sky where the Moon is a distant, smaller companion. This reminds us that even the most reliable celestial rhythms are slowly changing, that the cosmic clockwork we depend on is gradually winding down. In 600 million years, the Sun's increasing luminosity will trigger Earth's final mass extinction. Picture a planet where temperatures have risen past the tolerance of most complex life, where only extremophiles survive in caves, deep underground, or near the poles. The sun brightens by about 10% every billion years as it ages, and in 600 million years, this increase will be enough to break down the carbonate-silicate cycle that regulates Earth's carbon dioxide levels. Research by astrobiologists at Penn State in 2013 shows that as this cycle fails, CO2 levels will plummet, plants will die, and the food chain will collapse. Oxygen levels will drop as photosynthesis ceases, and the atmosphere will become unbreathable for animals. The age of complex life, which began 540 million years ago in the Cambrian explosion, will end, bringing Earth's biological experiment full circle. To think that the same stellar aging that allows life also ensures its eventual death. In 800 million years, Saturn's rings will have completely disappeared. Imagine looking up at Saturn from one of its moons and seeing only a naked planet. The magnificent rings that defined it for billions of years now scattered into space or fallen into the atmosphere. Studies by NASA scientists in 2018 using data from the Cassini spacecraft show that Saturn's rings are being destroyed by ring rain, with particles spiraling into the planet's atmosphere at a rate of several tons per second. The rings, which may have formed only 100 million years ago, will last less than another billion years. Any civilization in the Saturn system will witness the slow dissolution of one of the solar system's most beautiful features. In a sense, even the grandest structures in space are temporary, glorious moments in an endless process of creation and decay. In 1 billion years, Earth's oceans will evaporate completely into space. Imagine a planet covered in cracked salt flats, dry riverbeds stretching across continents, the last traces of water locked in minerals far underground. As the sun brightens, water vapor in the atmosphere will rise high enough for ultraviolet light to break it into hydrogen and oxygen. The hydrogen, being light, escapes into space, lost forever. Climate models by researchers at the Institute Pierre Simon Laplace in 2013 show that Earth will lose its oceans within 1 to 1.5 billion years, transforming into a desert world. Any remaining life will be microbial, surviving in the deep subsurface where groundwater still exists. The blue marble we know will become a red one, more like Mars than the Earth of today. This reminds us that water, the essence of life as we know it, is not a permanent gift but a temporary blessing that can be stripped away. In 1.5 billion years, any remaining photosynthetic organisms will go extinct. Picture a world where the green that once covered continents has vanished entirely, where the last algae and bacteria have died, where the primary source of oxygen production has ceased. As carbon dioxide levels drop below the minimum needed for photosynthesis, plants will be unable to survive. Studies by Jack O'Malley James at the University of St Andrews in 2013 show that even C4 plants, which are more efficient at capturing CO2, will fail when atmospheric levels drop below 10 parts per million. Without photosynthesis, the oxygen atmosphere we breathe will slowly disappear, consumed by geological processes like rock weathering and volcanic gases. The air will become thin, nitrogen-rich, and toxic. To think that the oxygen we breathe, produced by life over billions of years, will vanish within a billion more, returning Earth to a state more like its ancient, pre-life atmosphere. In 2 billion years, the Milky Way's disk will begin to noticeably warp from the approach of Andromeda. Imagine looking up at night and seeing the galactic plane bent like a warped record. Stars clustering in strange patterns, the familiar spiral structure distorted by gravitational tides. Simulations by NASA astrophysicists in 2012 show that long before the actual collision, Andromeda's gravity will begin pulling at the Milky Way's outer stars and gas clouds. The two galaxies will exchange material, triggering bursts of star formation in the regions where they interact. From Earth, if the planet still exists, the night sky will gradually fill with more and more stars as Andromeda looms larger. In a sense, our cosmic address is about to change. Our quiet corner of the universe about to become the site of one of nature's most spectacular collisions. In 2.3 billion years, Earth's magnetic field may shut down permanently. Picture a planet without its protective shield, where solar wind strips away the atmosphere molecule by molecule, where radiation levels on the surface make life impossible. The Earth's magnetic field is generated by convection in the molten iron core. But as the core cools over billions of years, this dynamo will eventually stop. Research by geophysicists at the University of California, Berkeley in 2016 suggests that Earth's core may solidify completely in 2 to 3 billion years. Without a magnetic field, the solar wind will erode the atmosphere as it did on Mars, and the planet will become airless and barren. The compass needles that guided explorers will spin aimlessly, pointing nowhere. This reminds us that the invisible forces protecting life are as vulnerable to time as everything else. In 2.8 billion years, Earth's surface temperature will reach 100 degrees Celsius, even in the shade. Imagine a world where water cannot exist as a liquid anywhere on the surface, where metal left in the sun would burn skin, where any remaining atmosphere is thick with steam and toxic gases. The sun's luminosity will have increased by nearly 30%, pushing Earth into a runaway greenhouse state. Studies by planetary scientist James Casting in 1993 show that once surface temperatures exceed the boiling point of water, the planet enters an irreversible feedback loop where more heat causes more evaporation, which causes more heat. Earth will resemble Venus, a hell of scalding temperatures and crushing atmospheric pressure. The planet that gave birth to billions of species will have killed its last inhabitant. To think that the same star that warmed the primordial soup will one day boil it away. In 3.5 billion years, Andromeda and the Milky Way will collide in earnest. Picture the sky filled with stars, so many that darkness between them almost disappears. New nebulae igniting in brilliant colors as gas clouds smash together, the galactic cores blazing like twin suns. Simulations show that the collision will last several 100 million years, with the galaxies passing through each other, then falling back together, merging into a single elliptical galaxy that astronomers have nicknamed Milkometa. From Earth, if it survives, the view would be spectacular. Night skies brighter than the full moon, stars forming in vast nurseries visible to the naked eye. Our solar system will likely be flung into a different part of the new galaxy, perhaps ending up in the halo far from the core. In a sense, this collision is not destruction but creation, two separate stories merging into one larger narrative. In 4 billion years, our solar system may be ejected from the merged galaxy entirely. Imagine the sun and its planets drifting alone in the intergalactic void. The galaxy receding behind us, the space between stars growing wider with each passing million years. During the Milky Way Andromeda merger, gravitational interactions will fling some stars out of the galaxy entirely. Studies by astrophysicist T.J. Cox in 2008 calculated that there is a small but non-zero chance our solar system will be ejected during the collision. If this happens, future astronomers would see a sky with no galactic band, only the distant glow of other galaxies, and they would live in a cosmic isolation we can barely imagine. To think that we might go from citizens of a bustling galaxy to exiles wandering the darkness between them. In 5 billion years, the sun will begin its transformation into a red giant. Imagine the sun swelling day by day, growing larger in the sky, its surface cooling to a dull red, but its total energy output increasing dramatically. As the sun exhausts hydrogen in its core, it will begin fusing hydrogen in a shell around the core, causing the outer layers to expand. Research by astrophysicist Klaus-Peter Schrader in 2008 shows that the sun will grow to 256 times its current diameter, engulfing Mercury and Venus completely. Earth's orbit may expand slightly due to the sun losing mass, but the intense radiation will vaporize anything remaining on the surface. Oceans will have been gone for billions of years by this point, but now even the rocks will melt. The planet that nurtured life for so long will become a cinder. This reminds us that even stars, the most enduring objects we know, have life cycles, and their deaths are as inevitable as their births. In 5.4 billion years, Earth will either be consumed by the sun or turned into a molten ball of lava. Picture the planet's surface glowing red hot, any remaining atmosphere stripped away, the crust melting and churning like a globe-spanning ocean of liquid rock. Calculations by astronomers at the University of Sussex in 2018 show that as the sun becomes a red giant, its outer layers will reach almost to Earth's current orbit. Whether Earth is actually swallowed depends on complex interactions between the sun's mass loss and orbital mechanics. If the planet survives, it will be uninhabitable, a scorched remnant orbiting a dying star. Everything that ever lived, every city ever built, every thought ever thought, will have been reduced to atoms mixed in molten rock. To think that our entire planetary history, from formation to death, is just one brief chapter in a much longer story. In 7 billion years, the sun will eject its outer layers and become a white dwarf. Imagine a star shrunk to the size of Earth, glowing white hot from residual heat, slowly cooling over trillions of years. The red giant phase will end when the sun sheds its outer envelope in a planetary nebula, leaving behind only the hot, dense core. Research published in 2016 by astronomers using the Hubble Space Telescope shows that white dwarfs cool predictably, fading from white to yellow to red to black over tens of billions of years. Any planets still orbiting will be frozen and dark, receiving barely any warmth from the ember that was once their sun. The solar system will become a tomb, planets circling a corpse in the darkness. In a sense, the death of the sun is the death of everything we've ever known, the final punctuation mark on a sentence that began 4.6 billion years ago. In 10 billion years, any frozen planets remaining in the solar system will be completely dark and cold. Picture Earth, if it still exists, as a frozen ball of rock and ice. Its surface temperature just a few degrees above absolute zero. Its sky black and starless, save for the faint glow of distant galaxies. The white dwarf sun will have cooled to a black dwarf, emitting no visible light, just infrared radiation too faint to warm anything. Studies by cosmologists show that planets orbiting dead stars will remain in stable orbits for trillions of years, but they will be lifeless, airless, and utterly cold. If any artifacts of humanity or its descendants somehow survived on Earth's surface, they would be perfectly preserved in the frozen darkness, monuments to a warm past that is now impossible to imagine. This reminds us that the warmth and light we take for granted are temporary, that the universe's natural state is cold and dark. In 20 billion years, all sun-like stars in the universe will have burned out. Imagine a cosmos where the familiar yellow stars that nurtured life are gone, replaced by either white dwarfs, neutron stars, or black holes. Only the smallest red dwarf stars will still burn, their dim light providing the last islands of warmth in an increasingly dark universe. Research by astrophysicist Fred Adams in 1997 shows that stars like the Sun have lifespans of about 10 billion years, and most were formed in the first few billion years after the Big Bang. By 20 billion years after the Big Bang, the era of sun-like stars will be over. Any civilizations existing then will orbit red dwarfs or find other sources of energy. To think that the type of star we think of as normal, the kind that lights our days, will become a rarity, then a memory, then a legend told in the darkness. In 100 billion years, the expansion of the universe will have carried distant galaxies beyond the observable horizon. Imagine astronomers of that distant era looking through telescopes and seeing nothing but their own galaxy and perhaps a few close neighbors. The rest of the universe vanished beyond the cosmic horizon. The accelerating expansion of space, driven by dark energy, is pushing distant galaxies away from us faster than light can travel. Research by cosmologist Lawrence Krauss in 2007 shows that within 100 billion years, all galaxies beyond our local group will be redshifted into invisibility. Future civilizations will have no evidence that the universe is expanding or that it began in a Big Bang. They will think they live in a small, static cosmos. They will be wrong, but they will have no way to know it. In a sense, we are lucky to live in an era where the universe reveals its history to us. That window is slowly closing. In 200 billion years, the universe will enter the black hole era, where stellar remnants outnumber living stars by millions to one. Imagine a cosmos transformed into a graveyard, white dwarfs cooling into black dwarfs, neutron stars spinning alone in the void, and black holes of all sizes drifting through space. Research by astrophysicist Fred Adams in 1997 shows that by this time, the last conventional stars will have exhausted their fuel. Only the longest-lived red dwarfs, those tiny miserly stars that burn for trillions of years, will still glow dimly. The universe will be darker than we can imagine, with vast distances between objects, and any civilization still surviving will need to cluster around the dying embers of the last red dwarfs or develop technologies to extract energy from black holes. To think that the age of starlight, which seemed eternal, is merely a brief flash in cosmic history. In 300 billion years, the last conventional stars will finally die, and star formation will have ceased entirely. Picture the final red dwarf in the universe, flickering out after burning for 300 billion years, having outlived the Sun by a factor of 30. Studies show that the smallest red dwarfs, with masses just 7 to 8% that of the Sun, are the universe's most efficient engines, converting their hydrogen into energy so slowly they can last hundreds of billions of years. When the last one dies, darkness will be nearly complete. Galaxies will be invisible unless two stellar remnants happen to collide, briefly flaring into light before fading again. The concept of a night sky filled with stars will be incomprehensible to any beings existing. Then they will know only darkness, punctuated by rare, fleeting glows. In a sense, the stellariferous era, the age of stars, will be remembered as the universe's golden age. In 400 billion years, the only sources of light will be white dwarf collisions and the accretion disks of black holes. Imagine a universe where light is so rare that a single collision between two white dwarfs, creating a brief Type Ia supernova, would be visible across a substantial portion of the observable universe. Research on stellar dynamics shows that even in this dark era, gravity will occasionally bring stellar corpses together. When white dwarfs collide, they can briefly reignite, shining with the light of billions of suns for a few weeks before fading forever. Black holes that capture matter, perhaps from passing clouds of dark matter or the rare stellar remnant, will create accretion disks that glow with X-rays. These will be the universe's lighthouses, rare beacons in an ocean of darkness. Any advanced civilization would navigate by these events, marking time by the intervals between cosmic flashes. In 500 billion years, galaxies will have lost most of their stars to evaporation, leaving only dense cores. Picture what were once magnificent spiral and elliptical galaxies reduced to small, tight clusters of stellar remnants around central supermassive black holes. Research on gravitational dynamics by Needham and Ostraker in 1997 shows that close encounters between stars, though individually, re-accumulate over hundreds of billions of years. Some stars gain enough energy to escape the galaxy entirely, while others fall toward the center. This process, called galactic evaporation, will scatter 90% of a galaxy's stars into intergalactic space over timescales of Yp to 1020 years. The beautiful structures we see in telescopes will be gone, replaced by dense cores of dead stars slowly spiraling into their central black holes. In a sense, galaxies are not eternal islands, but temporary gatherings that will eventually dissolve. In 600 billion years, proton decay may begin to erase ordinary matter itself. If protons are not stable, imagine matter simply ceasing to exist, not through any dramatic explosion, but through the slow, random decay of protocols into lighter particles. The stability of protons is one of physics' deepest questions. Current experiments have set the lower limit for proton half-life at about 1034 years, but some grand unified theories predict they will eventually decay. If protons decay, then after 1040 years or so, all ordinary matter, the atoms that make up dead stars, planets, and any remaining structures, will slowly dissolve into radiation. White dwarfs will evaporate, neutron stars will crumble, and even black holes will be surrounded by nothing but empty space and faint gamma rays. To think that the very substance of reality might be temporary, that even atomic nuclei have lifespans, challenges everything we think about permanence. In 700 billion years, brown dwarfs will collide occasionally, creating brief flashes of fusion in the darkness. Picture two failed stars, objects that never quite ignited, drifting through space for hundreds of billions of years until chance brings them together. Studies show that brown dwarfs, too small to sustain hydrogen fusion, slowly cool over time, eventually becoming cold, Jupiter-like worlds. But when to collide, their combined mass might briefly exceed the fusion threshold, creating a dim red dwarf that burns for a few billion years before dying. These collisions will be incredibly rare, perhaps one every trillion years in a region the size of our X-galaxy, but they will represent the universe's last gasps of star formation. Any observers would see a sudden light appear in the darkness, slowly brightening, then fading over geological timescales. In a sense, even in death, the universe tries to remember what it was like to be young. In 800 billion years, the cosmic microwave background radiation will have cooled to just above absolute zero. Imagine the afterglow of the Big Bang, which currently bathes the universe in 2.7 Kelvin microwave radiation, cooled to a mere fraction of a degree above absolute zero. Research shows that as the universe expands, this radiation is redshifted to longer and longer wavelengths, becoming colder and colder. By 800 billion years, it will have cooled to perhaps 0.3 Kelvin, making the universe's ambient temperature colder than the coldest laboratories we can create today. This means any object in intergalactic space will naturally cool to nearly absolute zero, with molecular motion almost completely stopped. The universe will be not just dark, but profoundly, unimaginably cold. To think that the warm radiation from the universe's birth will one day be indistinguishable from the void itself. In 900 billion years, neutron stars will have cooled to temperatures below 5 Kelvin, becoming dark matter. Picture these incredibly dense stellar corpses, each packing 1.4 solar masses into a sphere just 20 kilometers across. Now radiating no heat, emitting no light, invisible except through their gravitational influence. Research on neutron star cooling shows they start at billions of degrees after formation but cool exponentially over time. By 900 billion years, their surface temperatures will be just a few degrees above absolute zero. They will be perfect spheres of degenerate matter, spinning in darkness, detectable only if something happens to pass near them. These objects, the crushed cores of once massive stars, will join the dark matter as invisible shapers of cosmic structure. In a sense, the universe is slowly erasing all evidence of its luminous past, converting everything that once shone into darkness. In 1 trillion years, the degenerate era will be in full swing, a universe of stellar corpses and black holes. Imagine a cosmos where the brightest objects are white dwarfs that glow only with residual heat, emitting less light than a modern LED bulb. Research by Adams and Laughlin defines this as the degenerate era, where degenerate matter white dwarfs and neutron stars dominates the universe's mass budget outside of black holes. Star formation has been dead for hundreds of billions of years. Galaxies have evaporated. The universe is cold, dark, and nearly empty, with vast distances between objects. Occasionally, two white dwarfs might merge, creating a brief supernova that illuminates a region of space for a few weeks. Any civilization surviving in this era would need to harvest the faint heat from white dwarfs, or more likely, extract energy from rotating black holes using advanced technology. To think that this desolate future will last far longer than the stelliferous Earther age of stars is just a brief introduction to a much longer, darker story. In 1.1 trillion years, white dwarfs will have cooled enough to crystallize completely into cosmic diamonds. Picture stellar corpses transforming into spheres of crystallized carbon and oxygen. The densest diamonds in the universe, each one containing a star's worth of mass. Research by astrophysicists in 2004 confirmed that white dwarfs crystallize from the inside out as they cool, forming a lattice structure like a giant diamond. These diamond stars will be completely dark, no longer emitting visible light, just faint infrared radiation. They will drift through space as perfect, eternal gems that no one will ever see or mine. If you could somehow stand on one, you would find a surface gravity 100,000 times stronger than Earth's, crushing you instantly. To think that the final form of most stars is to become treasure beyond imagining, hidden in eternal darkness. In 1.2 trillion years, the last planetary nebulae will have faded completely from view. Imagine the beautiful glowing clouds that once surrounded dying stars' objects, like the Ring Nebula and the Helix Nebula, now so dispersed and dim that they're indistinguishable from empty space. Research shows that planetary nebulae only remain visible for about 10,000 to 50,000 years after formation, before expanding and fading by 1.2 trillion years. Even the youngest nebulae from the last dying stars will have dissipated entirely. The universe will have lost these colorful reminders of stellar death, these cosmic flowers that bloomed briefly in the darkness. Any observer would see only darkness, with no evidence that stars once shed their outer layers in spectacular displays. In a sense, the universe is erasing even the monuments to its stellar age. In 1.3 trillion years, orbits within dense stellar remnant clusters will begin decaying through gravitational wave emission. Picture two neutron stars, or white dwarfs, locked in mutual orbit for 1 trillion years, now slowly spiraling toward each other as they radiate away their orbital energy in the form of gravitational waves. Research on binary systems shows that gravitational radiation is incredibly weak for normal stellar orbits, but over trillion-year timescales, even wide orbits will eventually decay. As the objects spiral inward, their orbital period shortens from thousands of years to days to hours to seconds, until finally they merge in a violent collision that releases more energy in a moment than a star produces in 1,000,000 years. These mergers will be the universe's last fireworks, rare flashes of light in the eternal night. To think that even the most stable orbits are temporary, doomed by the mathematics of curved spacetime. In 1.4 trillion years, the last brown dwarfs will have cooled below the freezing point of water. Imagine objects that were once considered failed stars, now colder than any planet, their atmospheres potentially harboring exotic ice crystals made of metallic compounds. Research shows that brown dwarfs cool continuously over time, never reaching an equilibrium temperature. By 1.4 trillion years, even the most massive brown dwarfs will have cooled to below 273 Kelvin, the freezing point of water. Their surfaces will be coated in exotic ices, perhaps methane, ammonia, or even stranger compounds formed under high pressure. They will be invisible in optical light, barely warm enough to emit faint infrared radiation. Any civilization would need infrared sensors just to know these objects exist. In a sense, the universe's coldest stars will be colder than Antarctica. In 1.5 trillion years, cosmic rays will be the only particles moving at relativistic speeds through empty space. Picture a universe where almost nothing moves quickly, no solar winds, no supernova shockwaves, no jets from active galaxies, just the occasional cosmic ray particle, accelerated long ago, still racing through the void at near light speed. Research on cosmic ray propagation shows that these high-energy particles can travel for billions of years before interacting with anything. By 1.5 trillion years, cosmic rays from ancient supernovas and the last active black holes will be the only fast-moving particles left. The universe will be not just dark and cold, but eerily still, with almost no motion except for these lonely, energetic particles traversing empty space. To think that the universe's frenetic energy will give way to an almost perfect stillness. In 1.6 trillion years, supermassive black holes will dominate the mass of their former galaxies. Imagine the black holes that once sat at galaxy centers, now containing more mass than all the stars and stellar remnants that remain bound to them combined. Research by astrophysicists shows that over trillions of years, supermassive black holes will accumulate mass through mergers and by capturing passing stellar remnants. Meanwhile, most stars will have evaporated from the galaxy through gravitational interactions. By 1.6 trillion years, each ancient galaxy core will be essentially a single enormous black hole with a sparse halo of dead stars and smaller black holes slowly spiraling inward. These black holes will be truly supermassive, perhaps containing the mass of hundreds of billions of suns. In a sense, galaxies will have been consumed by their own centers, eaten from within by the monsters they harbored. In 1.7 trillion years, neutrino background radiation will have cooled to just 0.0003 Kelvin above absolute zero. Picture the ghostly particles that barely interact with matter. The cosmic neutrino background from the Big Bang, now carrying almost no energy at all. Research shows that neutrinos, like photons, are redshifted by cosmic expansion. The cosmic neutrino background, which currently has a temperature of about 195 Kelvin, will have cooled to less than 1,000th of a degree above absolute zero. These neutrinos will still permeate all of space, billions in every cubic centimeter, but they will have so little energy that they will almost never interact with anything. The universe will be filled with these phantom particles, invisible witnesses to a cosmos that has grown cold. To think that even the most elusive particles will eventually lose their energy to the expanding void. In 1.8 trillion years, any remaining asteroids will have been swept up by planets or ejected from systems. Imagine dead solar systems finally clearing out their debris fields after trillions of years of orbital chaos. Research on long-term orbital stability shows that asteroid belts are not stable on these timescales. Close encounters with planets will either send asteroids crashing into planetary surfaces or fling them into interstellar space. By 1.8 trillion years, the last rocks and ice chunks will have been removed, leaving only planets in relatively circular orbits around dead stars. The messy, dynamic systems we know will have been cleaned out, leaving behind only the most stable configurations. In a sense, the universe is a patient housekeeper, eventually tidying up every system. In 1.9 trillion years, the infrared glow from cooling stellar remnants will become undetectable by any conventional means. Picture a universe so dark that even infrared telescopes, the tools that can see through dust and detect the coldest objects, would find almost nothing to observe. Research on white dwarf cooling shows that after about 2 trillion years, white dwarfs will have cooled to below 200 Kelvin colder than the coldest natural temperature on Earth. At these temperatures, they emit so little thermal radiation that detecting them would require impossibly large telescopes or proximity measurements. The universe will have become truly, utterly dark, with only the rare merger or accretion event providing any light. To think that darkness is not just the absence of light, but the universe's natural state, and light was only a temporary aberration. In 2 trillion years, close encounters between stellar remnants will eject 90% of objects from their galactic halos. Picture what remains of galaxies now, just dense cores of stellar corpses around supermassive black holes slowly evaporating as objects gain enough energy to escape into intergalactic space. Research by Needham and Ostraker shows that gravitational interactions in dense stellar systems cause some objects to gain energy while others lose it. The high-energy objects escape while the low-energy ones sink toward the center. Over 2 trillion years, this process will scatter most stellar remnants into the void, leaving only the densest cores. These ejected objects will wander intergalactic space forever, never to encounter another object again. In a sense, even the gravitational bonds holding the remnants of galaxies together will dissolve, and the universe will become even more empty. In 2.1 trillion years, the final molecular clouds in the universe will dissipate, ending any possibility of star formation forever. Imagine vast nebulae that once glowed with the birth of stars, now reduced to scattered atoms drifting in endless darkness. their gravitational cohesion lost to the relentless expansion of space. Research from the Harvard-Smithsonian Center for Astrophysics indicates that molecular clouds require specific densities and temperatures to remain stable, conditions that will become impossible as the universe continues to expand and cool. These clouds, composed primarily of hydrogen and helium molecules, will be torn apart by cosmic radiation and the stretching of space itself. The Orion Nebula, once a stellar nursery spanning 24 light-years, represents the kind of structure that will have vanished entirely by this epoch. To think that the universe's creative phase, its ability to forge new suns, will have ended completely, leaving only the slow decay of what already exists. In 2.2 trillion years, the supermassive black holes at galactic cores will accelerate their consumption of the remaining stellar remnants in their vicinity. Picture the central region of what was once the Milky Way, now just a supermassive black hole surrounded by a sparse halo of white dwarfs and neutron stars, slowly spiraling inward like leaves caught in an invisible drain. Simulations by astrophysicist Avi Loeb at Harvard show that gravitational wave radiation causes orbiting objects to lose energy over vast timescales, eventually causing them to merge with the central black hole. A white dwarf orbiting at 1 light-year from a supermassive black hole will take trillions of years to spiral inward, but the process is inexorable. When these remnants finally cross the event horizon, they add their mass to the black hole without any visible display. No light, no explosion, just silent disappearance. This reminds us that even gravity's patient embrace has an ending, a final merger into darkness. In 2.3 trillion years, the cosmic microwave background radiation will have redshifted to wavelengths exceeding several meters, making it effectively undetectable. Imagine the ancient light from the Big Bang, once visible as a faint glow at microwave frequencies, now stretched into radio waves so long and faint that no natural process could distinguish them from the quantum vacuum itself. Calculations by cosmologist Lawrence Krauss demonstrate that as space expands, all electromagnetic radiation stretches proportionally, with the CMB cooling from its current 2.7 Kelvin to less than 0.001 Kelvin. This relic radiation, which has traveled for over 13 billion years and serves as our window into the infant universe, will become indistinguishable from nothingness. Any civilization existing at this epoch would have no evidence that the universe ever had a hot, dense beginning. It is humbling to realize that even the most ancient light in existence will fade into obscurity, erasing the very evidence of cosmic origins. In 2.4 trillion years, gravitational interactions will have ejected approximately 95% of all stellar remnants from their galactic cores into intergalactic voids. Picture a white dwarf, once part of a dense stellar cluster, now cast out into the expanding emptiness between galaxy remnants, traveling at hundreds of kilometers per second with no destination and no possibility of ever encountering another object. Research published in the Astrophysical Journal by Kallmeyer and Gould in 2007 shows that three-body gravitational encounters in dense stellar systems result in one object gaining enough velocity to escape while the others become more tightly bound. Over 2.4 trillion years, repeated interactions will eject the vast majority of objects, leaving only the most tightly bound remnants near the central black hole. These ejected stellar corpses will drift through space for the remaining lifetime of the universe, solitary wanderers in an ever-expanding cosmos. To think that even the gravitational communities that once were galaxies will be scattered to the cosmic winds, each remnant alone forever. In 2.5 trillion years, brown dwarfs will have cooled to temperatures below 200 Kelvin, colder than the coldest natural temperatures on Earth. Imagine these failed stars, objects with masses between 13 and 80 times that of Jupiter, now radiating so little energy that they would appear as absolutely black spheres against the darkness of space, visible only by their gravitational effects. Studies by Adam Burrows at Princeton show that brown dwarfs cool steadily over time, their internal heat gradually radiating away with no fusion reactions to replenish it. A brown dwarf with 50 Jupiter masses, which might have glowed faintly in infrared when young, will by this epoch emit radiation only in the far infrared and microwave spectrum at incredibly low levels. These objects represent the universe's forgotten masses, too small to ignite as stars but too large to be planets, now cooling into invisible darkness. In a sense, they are cosmic ghosts, present but imperceptible, holding mass but releasing almost nothing into the void. In 2.6 trillion years, the last globular clusters will have completely dissolved through stellar evaporation. Picture Omega Centauri, currently home to approximately 10 million stars packed into a sphere just 150 light-years across, now reduced to scattered stellar remnants spread across thousands of light-years of space. Research by Princeton astrophysicist Michael Schara demonstrates that globular clusters evaporate as stars occasionally gain enough velocity through gravitational encounters to escape the cluster's gravity well. Over 2.6 trillion years, even the most massive and tightly bound clusters will lose all their members. The beautiful spherical concentrations of stars that once orbited galaxies like ancient cities will have dispersed completely, their constituent white dwarfs and neutron stars wandering individually through the cosmic void. This reminds us that even structures that have persisted for most of cosmic history are temporary, subject to the patient unraveling of gravitational dynamics. In 2.7 trillion years, any remaining planet-sized objects will have experienced enough cosmic ray bombardment to alter their surface compositions significantly. Imagine a frozen world, perhaps once a rogue planet ejected from its solar system billions of years ago. Its surface now scarred and chemically transformed by trillions of years of high-energy particle impacts. Studies by NASA researchers show that cosmic rays continuously strike objects in space, with each impact capable of breaking molecular bonds and triggering nuclear reactions in surface materials. A rocky planet exposed to cosmic rays for 2.7 trillion years would have its outer layers completely processed, with surface atoms displaced and mixed to depths of several meters. These worlds, if any remain intact, would bear surfaces unlike anything in our current universe, sculpted entirely by radiation rather than geology. It is humbling to consider that even solid worlds are not permanent, but slowly eroded by the invisible rain of particles crossing the cosmos. In 2.8 trillion years, the separation between the few remaining bound structures will have increased to an average of several billion light-years. Picture the sparse galactic cores that still retain a few stellar remnants around their central black holes, now separated by voids so vast that light would take billions of years to cross the emptiness between them. Calculations based on the lambda-CDM cosmological model show that dark energy continues to accelerate cosmic expansion, pushing structures apart at ever-increasing rates. Galaxy cores that might now be separated by hundreds of millions of light-years will be billions of light-years apart, with the space between them expanding faster than light can cross it. Any observer in one structure could never receive signals from another, even in principle, as the expansion of space would stretch electromagnetic waves beyond any possibility of detection. To think that the universe will have fragmented into completely isolated pockets of matter, each alone in an expanding void, forever cut off from all others. In 2.9 trillion years, white dwarfs will have cooled to crystallization temperatures throughout their entire interiors. Imagine stellar remnants the size of Earth, composed almost entirely of carbon and oxygen atoms, now arranged in perfect crystalline lattice from core to surface, cosmic diamonds drifting through space. Research published in Nature in 2019 by Tremblay and colleagues confirmed that white dwarfs crystallize as they cool below approximately 10,000 Kelvin, releasing latent heat that slightly slows their cooling. A typical white dwarf takes roughly 10 billion years to begin crystallizing and another trillion years to crystallize completely. By 2.9 trillion years, even the youngest white dwarfs from the last generation of stars will have transformed into completely solid crystals, no longer containing any liquid layers. These crystallized remnants will continue cooling toward absolute zero over the incomprehensible ages to follow. In a sense, stars do not truly die but transform. Their final form, that of frozen, perfect gems, containing the ashes of nuclear fusion. In 3 trillion years, the last gravitationally bound systems will contain only a handful of objects orbiting supermassive black holes. Picture what remains of a galaxy's core, perhaps just 3 or 4 white dwarfs in distant orbits around a black hole billions of times the mass of the Sun. The final survivors of gravitational evaporation that scattered all their companions. Simulations by Milos Milosavljevic at the University of Texas show that gravitational systems decay through a process where objects exchange energy, with some gaining enough to escape while others become more tightly bound. After 3 trillion years of this process, typically only a few % of the original objects remain bound. These final remnants orbit in a space that is otherwise completely empty. No gas, no dust, no light, just darkness and the invisible pull of gravity. This reminds us that even the most massive structures in the universe will eventually be reduced to nearly nothing. Tiny islands of matter in an ocean of expanding emptiness. In 3.1 trillion years, the quantum vacuum fluctuations will become the dominant source of energy in the universe, exceeding all radiation from remaining matter. Imagine space itself producing tiny, spontaneous bursts of energy that appear and vanish in fractions of a second, now more energetic than the faint glow from all stellar remnants combined. Research by physicists at the University of Cambridge shows that quantum mechanics requires empty space to contain fluctuating electromagnetic fields with an energy density that remains constant even as the universe expands. A cubic meter of vacuum space contains virtual particles continuously popping in and out of existence, contributing roughly 10 to the -9 joules of energy. As matter-based radiation redshifts toward zero, these quantum fluctuations will dominate, making the vacuum itself more energetic than physical objects. To think that emptiness will become more substantial than matter, that nothingness will outshine the fading remnants of stars. In 3.2 trillion years, neutron stars will have cooled to temperatures below 100 Kelvin, making them among the coldest macroscopic objects in existence. Picture a sphere just 20 kilometers across, but containing 1.4 times the mass of the Sun, now radiating so little heat that its surface temperature barely exceeds the coldest depths of intergalactic space. Studies by Danny Page at the National Autonomous University of Mexico demonstrate that neutron stars cool through neutrino emission for the first million years, then through photon radiation for billions of years thereafter. a typical neutron star born at 1 trillion Kelvin will have cooled to room temperature after approximately 100 billion years and continues cooling asymptotically toward absolute zero by 2 trillion years. These incredibly dense remnants will be nearly as cold as the cosmic background, invisible spheres of degenerate matter drifting through darkness. In a sense, the most extreme objects born from stellar violence will have fallen silent and cold. Their incredible density, the only testament to their fiery origins. In 3.3 trillion years, the expansion of space will have stretched the wavelength of any photons traveling through intergalactic voids to dimensions exceeding thousands of kilometers. Imagine a single photon emitted by a stellar remnant, its wave now so elongated that it would span the distance of a small country on Earth, carrying almost no energy whatsoever. Calculations based on Hubble's law show that electromagnetic radiation redshifts proportionally to the expansion factor of the universe, with wavelengths stretching as space itself expands. A photon that began as visible light would, after 3.3 trillion years of traveling through expanding space, have its wavelength stretched by factors of millions or billions. These ultra-long wavelength photons carry energies approaching the quantum mechanical lower limit, making them nearly indistinguishable from the vacuum itself. This reminds us that even light, traveling at the universe's speed limit, cannot escape the effects of cosmic expansion, eventually stretching into near-nothingness. In 3.4 trillion years, the average density of matter in the observable universe will have decreased to less than 1 proton per cubic light-year. Picture a volume of space the size of the distance light travels in a year, containing nothing but a single hydrogen atom, with the nearest other atom more than a light-year away in any direction. Research published by cosmologists at the Max Planck Institute shows that as the universe expands, matter density decreases proportionally to the cube of the expansion factor. Currently, the universe contains roughly 1 hydrogen atom per cubic meter on average. But this will dilute to almost unimaginable sparseness. A cubic region with edges 1 light-year long, encompassing about 10 to the 45 cubic meters, will contain just a single atom. Any remnant of structure will be separated by voids so empty that matter becomes a statistical rarity rather than a cosmic commonplace. It is humbling to realize that the universe will transform from a place filled with galaxies to a place where atoms themselves are lonely, outliers in infinite emptiness. In 3.5 trillion years, gravitational wave background radiation will have redshifted beyond any possible means of detection. Imagine ripples in spacetime itself, created by merging black holes billions of years ago, now stretched to wavelengths spanning multiple galaxies and carrying energies too small to measure even in principle. Studies by LIGO researchers demonstrate that gravitational waves, like electromagnetic radiation, are subject to cosmological redshift as space expands. Waves that might have had frequencies of hundreds of hertz when generated will have been stretched to frequencies of 10 to the negative 20 hertz or lower, with wavelengths of billions of light years. The energy carried by these waves becomes vanishingly small, approaching the fundamental limits imposed by quantum mechanics. These ancient echoes of cosmic violence will have faded into the quantum noise of space-time itself. To think that even the fabric of space carries memories that eventually dissolve, that the universe erases its own history through expansion. In 3.6 trillion years, any asteroid-sized objects remaining from ancient solar systems will have been ground to dust by micrometeorite bombardment. Picture a rocky body, perhaps once part of an asteroid belt orbiting a star that died a trillion years ago. now reduced to a dispersing cloud of microscopic particles after eons of collisions. Research by planetary scientists at MIT shows that small bodies in space are continuously impacted by even smaller particles, with each collision ejecting material and slowly eroding the object. An asteroid 10 kilometers across, subjected to constant bombardment for 3.6 trillion years, would be completely pulverized, its atoms scattered across light years of space. The rubble of old worlds, the fragments of shattered moons, all will have been ground to atomic dust by the patient hammer of endless impacts. In a sense, even rocks are not permanent, but slowly disintegrate under the universe's erosive processes, returning to the cosmic dust from which they formed. In 3.7 trillion years, supermassive black holes will have accreted virtually all matter remaining in their gravitational sphere of influence. Imagine the black hole that once anchored the Milky Way, now perhaps 10 billion solar masses, having consumed every stellar remnant that remained bound to it, sitting alone in absolute darkness. Calculations by Kip Thorne show that objects orbiting black holes gradually lose orbital energy through gravitational wave emission and eventually spiral inward over immense timescales. A white dwarf orbiting 100 light-years from a supermassive black hole will take trillions of years to merge. But given enough time, all bound objects will fall in. By 3.7 trillion years, these feeding frenzies will have largely concluded, leaving black holes that have grown somewhat larger but are now surrounded by complete emptiness. These gravity wells will have cleared their neighborhoods entirely, cosmic vacuum cleaners that have swept up the last crumbs of matter. This reminds us that black holes represent not just destruction, but a kind of cosmic tidiness, gathering and concentrating matter into singular points. In 3.8 trillion years, the cosmic neutrino background will have cooled to temperatures below 1/1,000,000th of a Kelvin. Picture the universe filled with ghost particles, neutrinos released in the first second after the Big Bang, now moving so slowly that they barely qualify as relativistic, their energies reduced to almost nothing by cosmic expansion. Research by John Bokel demonstrated that neutrinos, despite having tiny masses, are affected by cosmic expansion just like photons. These particles, which outnumber protons by roughly 1 billion to 1, currently have temperatures around 1.9 Kelvin, but will continue cooling as space expands. By 3.8 trillion years, they will move at speeds much slower than light, their wavelengths stretched 2 kilometers, carrying negligible energy. Any civilization attempting to detect them would find the task nearly impossible, as their interaction probability decreases with their energy. It is humbling to consider that even the most abundant particles in the universe will fade into practical non-existence, present but undetectable. In 3.9 trillion years, white dwarf stars will have dimmed to the point where they emit less light than a small candle on Earth. Imagine a stellar remnant with the mass of the Sun compressed into an Earth-sized sphere, now glowing so faintly that it would be invisible to human eyes even from just a few meters away. Studies by the Sloan Digital Sky Survey team show that white dwarfs cool steadily, following a predictable luminosity curve as they radiate their remaining thermal energy. A white dwarf that once glowed with surface temperatures of 100,000 Kelvin will have cooled to, perhaps, 1,000 Kelvin by this epoch, emitting primarily in the far infrared with total power output of just a few watts. These dying embers of stars that once blazed with the power of billions of hydrogen bombs will have become cosmic nightlights, barely distinguishable from the darkness around them. To think that stellar remnants will spend far more time as cold, dark objects than they ever spent as bright, living stars. In 4 trillion years, the density of dark energy will exceed the density of all matter in the universe by a factor of more than 1,000,000 to 1. Picture the universe as a space where the repulsive force of dark energy completely dominates, pushing everything apart with a strength that dwarfs the gravitational attraction between any remaining matter. Measurements from the Planck satellite show that dark energy currently comprises about 68% of the universe's energy density, with matter making up about 32%. As the universe expands, matter density decreases, while dark energy density remains constant, causing dark energy to become increasingly dominant. By 4 trillion years, matter will be so diluted that its gravitational effects become negligible compared to the accelerating push of dark energy. The cosmos will be a place where expansion overwhelms attraction, where isolation is not just common but guaranteed by the fundamental forces governing reality. In a sense, the universe will have chosen expansion over structure, dispersal over congregation. In 4.1 trillion years, the last planetary nebulae shells will have dispersed completely into the interstellar medium, their glowing gases now scattered across light years of space. Imagine the beautiful rings and structures that once surrounded dying stars. Formations like the Helix Nebula spanning several light-years, now expanded and diluted until no trace of their original shape remains. Research by astronomer Bruce Ballack at the University of Washington shows that planetary nebulae expand at velocities of 20 to 40 kilometers per second, gradually spreading their material across space. A nebula shell that began with a radius of 1 light-year will have expanded to hundreds of light-years over 4 trillion years, its density dropping to the point where it becomes indistinguishable from the surrounding vacuum. These monuments to stellar death, once brilliant displays of ionized gas, will have faded into nothingness, their atoms joining the diffuse background. This reminds us that even the most spectacular cosmic structures are temporary exhibitions, performances that play out over eons before dissolving into the backdrop. In 4.2 trillion years, gravitational microlensing events will become extraordinarily rare as stellar remnants drift farther apart. Picture 2 white dwarfs passing within a light-year of each other, a chance alignment that would cause one to briefly magnify the faint light of the other through gravitational lensing, an event that might occur once every trillion years in a given region. Studies by Bohdan Baczynski established that microlensing requires precise alignment between observer, lens, and background object, with probability decreasing as object density decreases. Currently, microlensing events in our galaxy occur regularly due to the high density of stars. But as remnants spread out and dim over trillions of years, such alignments will become vanishingly rare. The universe will have become so empty that even gravity's ability to bend light will rarely manifest in observable ways. To think that phenomena we currently study regularly will become once per trillion year accidents, cosmic rarities in an increasingly barren universe. In 4.3 trillion years, any remaining molecular hydrogen will have been dissociated into individual atoms by cosmic ray impacts. Imagine H2 molecules, the most common molecule in the current universe, now broken apart into separate hydrogen atoms that drift independently through space. Research published in the Astrophysical Journal by Stecker and Williams shows that cosmic rays continuously bombard molecules, occasionally striking with enough energy to break chemical bonds. Over 3 trillion years of exposure, virtually every molecular hydrogen bond will have been broken at least once. and the universe will be too sparse and cold for atoms to recombine. A region of space that might once have contained molecular clouds will now contain only isolated atoms, chemically inert and unable to form new structures. The universe will have forgotten chemistry entirely, retaining only the simplest atomic forms. In a sense, the cosmos will have regressed to a simpler state than even the early universe, which at least had the density and energy to forge molecules. In 4.4 trillion years, black dwarfs will begin to dominate the mass inventory of the universe, outnumbering all other objects combined. Picture stellar remnants, so cold they emit no detectable radiation, completely black spheres of crystallized carbon and oxygen floating unseen through space, the final form of stars like our Sun. Calculations by Fred Adams at the University of Michigan show that white dwarfs become black dwarfs after cooling for approximately 10 to 15 billion years, depending on mass. By 4.4 trillion years, even the youngest white dwarfs will have crossed this threshold, and these dark objects will comprise the vast majority of baryonic matter in the universe. Each one represents the compressed core of a star that once shone for billions of years, now silent and invisible. These objects will persist essentially unchanged for timescales that make trillions of years seem brief. This reminds us that the universe's long-term destiny is dominated not by light but by darkness, by objects that have exhausted all capacity to shine. In 4.5 trillion years, the rotation of galactic-scale black holes will have slowed measurably due to Hawking radiation, preferentially carrying away angular momentum. Imagine a supermassive black hole spinning at a significant fraction of the maximum possible rate, its rotation gradually decreasing as emitted radiation carries away rotational energy along with mass. Research by Stephen Hawking and subsequent work by Don Page shows that rotating black holes lose angular momentum faster than mass through quantum radiation effects at their event horizons. A black hole with 10 billion solar masses spinning rapidly will have lost a tiny but measurable fraction of its angular momentum over 4.5 trillion years. This process is extraordinarily slow, but given sufficient time, even these cosmic gyroscopes will eventually slow their spin. To think that even black holes, the universe's most permanent structures, are subject to gradual decay, losing not just mass, but their very rotation to the quantum vacuum. In 4.6 trillion years, any remaining iron-rich stellar remnants will show measurable surface erosion from dark matter particle collisions. Picture a neutron star with an iron-rich crust, its surface atoms occasionally struck by dark matter particles that pass through ordinary matter like ghosts, very rarely interacting but accumulating effects over vast timescales. Studies by Catherine Fries at the University of Texas suggest that dark matter particles, though weakly interacting, will occasionally collide with atomic nuclei in dense objects. Over 4.6 trillion years, these rare collisions will have displaced surface atoms, creating a kind of weathering effect on stellar remnants. A neutron star's surface might lose micrometers of material through this process, eroded by invisible particles that comprise most of the universe's mass. The universe's hidden matter will have left its mark on visible matter through patient, quantum-level bombardment. In a sense, even the distinction between dark and normal matter will blur over cosmic timescales, as one gradually shapes and erodes the other. In 4.7 trillion years, the cosmic web's large-scale structure will have completely dissolved as dark energy stretches space beyond the point where gravity can maintain any connections. Imagine the filaments and sheets of galaxy clusters that once spanned hundreds of millions of light-years now torn apart as the space between them expands faster than gravity can pull. Research by the Millennium Simulation Project showed how dark energy eventually overcomes gravity on cosmological scales. Structures that are not gravitationally bound at the local level will be pulled apart by cosmic expansion, with the separation between them growing exponentially. By 4.7 trillion years, even the largest structures in the universe will have been scattered, each galactic core isolated in its own expanding bubble of space-time. The cosmic web that took billions of years to form will have been erased entirely. This reminds us that structure itself is temporary in an accelerating universe. A brief phase between initial smoothness and final isolation. In 4.8 trillion years, proton-proton collision rates in the remaining gas will have dropped to less than 1 collision per cubic light-year per trillion years. Picture the incredibly sparse hydrogen atoms that still exist, now separated by such vast distances that they might drift for 1 trillion years without encountering another atom. Calculations based on kinetic theory show that collision rates depend on particle density and velocity, both of which decrease as the universe expands and cools. Currently, atoms in interstellar space might collide every few years within a given volume, but as density drops and temperature falls, collision rates plummet exponentially. By 4.8 trillion years, the universe will be so empty that atomic interactions become extraordinary events rather than common occurrences. Chemistry, which requires atoms to interact, will have effectively ceased to exist anywhere in the cosmos. To think that the universe will have become too sparse for atoms to find each other, even over billions of years of searching. In 4.9 trillion years, gravitational wave emission will have circularized the orbits of any remaining binary systems to near-perfect circles. Imagine two white dwarfs orbiting each other, their elliptical dance gradually smoothed by the emission of gravitational waves that carry away the orbital energy associated with eccentricity. Research by Peters and Matthews in 1963 established that gravitational radiation circularizes orbits over time, with eccentricity decreasing faster than orbital separation. A binary system that began with an eccentric orbit will have that eccentricity reduced by orders of magnitude over 4.9 trillion years, leaving the objects in nearly circular orbits. This process represents gravity smoothing out irregularities in its own field, polishing orbital dynamics through the emission of space-time ripples. These perfected orbits will continue to decay, but they will do so in the most symmetric way possible. In a sense, the universe exhibits a tendency toward mathematical elegance, grinding away orbital irregularities until only pure circular motion remains. In 5 trillion years, the event horizons of supermassive black holes will have grown by less than 1% through Hawking radiation absorption exceeding emission. Picture a black hole with billions of solar masses, so massive that it actually gains mass by absorbing cosmic microwave background photons faster than it loses mass through Hawking radiation. Calculations by Don Page show that black holes with masses above approximately 100,000 solar masses currently absorb more radiation from the CMB than they emit, causing them to grow very slightly. As the CMB continues to cool with cosmic expansion, this balance will eventually shift, but for the first 5 trillion years, the most massive black holes will actually increase in mass. A 10 billion solar mass black hole might gain several million solar masses over this period, a tiny fraction of its total mass, but a measurable change nonetheless. This represents one of the few growth processes remaining in the universe's future. This reminds us that even in an era of decay, the largest objects will briefly continue to grow. delaying their ultimate evaporation by incomprehensible times. In 5.1 trillion years, the velocity dispersion of ejected stellar remnants will have carried some objects more than 10 million light-years from their original galactic cores. Imagine a white dwarf ejected from its galaxy 3 trillion years ago, now traveling at 500 kilometers per second through intergalactic space, having covered distances that would span dozens of present-day galaxies. Studies by Nedin and Ostrika on stellar dynamics show that gravitational ejections can impart velocities ranging from hundreds to thousands of kilometers per second. An object traveling at 500 kilometers per second for 5 trillion years will have covered approximately 15 million light-years, a distance greater than the separation between the Milky Way and Andromeda today. These wanderers will never return, never encounter another object, never experience anything but endless motion through ever-expanding emptiness. To think that some stellar remnants will have journeyed distances that eclipse the scale of entire galaxy clusters, solitary travelers on voyages without destination. In 5.2 trillion years, quantum tunneling will have caused measurable decay in the nuclei of heavy elements within stellar remnants. Picture atoms of iron or nickel within a white dwarf's crystalline structure, their nuclei occasionally undergoing spontaneous fission through quantum tunneling despite being classically stable. Research by Freeman Dyson suggests that all atomic nuclei, given sufficient time, will eventually decay through quantum mechanical processes. An iron-56 nucleus, normally stable, has a minute probability of tunneling to a lower energy state by splitting or emitting particles. Over 5.2 trillion years, a measurable fraction of heavy nuclei in stellar remnants will have decayed, slowly transforming their composition. A white dwarf, initially composed of carbon and oxygen, will have trace amounts of helium and hydrogen from nuclear decay products. The universe will have begun the extraordinarily slow process of disassembling atomic nuclei through quantum effects. In a sense, even the stability of matter itself is temporary, subject to quantum uncertainty given infinite patience. In 5.3 trillion years, magnetic fields of isolated neutron stars will have decayed to strengths below 1/1,000,000th of their initial values. Imagine a neutron star that once possessed magnetic fields of 1,000,000,000 Gauss, among the strongest fields in the universe, now diminished to mere millions of Gauss through resistive decay. Studies by Christopher Thompson show that neutron star magnetic fields decay over timescales of millions to billions of years through the ohmic dissipation of electrical currents in the star's crust. By 5.3 trillion years, even the strongest magnetar fields will have faded to a tiny fraction of their original strength. These magnetic fields, which once powered spectacular X-ray flares and radio emissions, will have become weak and unremarkable. The neutron star's last connection to its violent birth will have faded almost entirely. This reminds us that even the most intense magnetic fields in nature are temporary, gradually bleeding away their energy over cosmic timescales until nothing remains but a faint ghost of former power. In 5.4 trillion years, the average kinetic energy of particles in intergalactic space will be less than 1/1,000,000th of an electron volt. Picture hydrogen atoms drifting through voids, moving so slowly that their velocities barely exceed a few meters per second, possessing almost no thermal energy. Research in statistical mechanics shows that particle kinetic energy scales with temperature, and as the universe expands and cools, average particle velocities decrease proportionally. Currently, particles in intergalactic space have kinetic energies corresponding to temperatures of a few Kelvin, but by 5.4 trillion years, this will have dropped 2/1,000,000ths of a Kelvin. At these energies, particles move in nearly classical trajectories, their quantum wave nature becoming more apparent than their particle nature. The universe will be filled with matter that barely moves, thermal motion reduced to the barest quantum minimum. To think that even motion itself will have nearly ceased, that particles will drift rather than fly, crawl rather than rush through the expanding void. In 5.5 trillion years, tidal forces from passing stellar remnants will have disrupted any remaining loosely bound binary systems. Imagine two white dwarfs orbiting each other at a distance of several light years, their tenuous gravitational bond suddenly broken when another remnant passes within a few light years, its gravity pulling the binary apart. Calculations by Jeans and later Heggie show that wide binaries are susceptible to disruption by passing objects, with disruption probability increasing over time as encounters accumulate. A binary system with components separated by 1 light-year has a high probability of disruption over 5.5 trillion years of exposure to chance encounters in their galactic core. The universe will have broken apart even these paired objects, ensuring that nearly all stellar remnants exist in isolation. These last companions will have been divorced by cosmic chance, leaving even fewer bound systems. In a sense, the universe enforces solitude, using random encounters to separate objects that once orbited together, ensuring that isolation becomes the cosmic norm. In 5.6 trillion years, cosmic ray energies will have decreased below levels capable of ionizing atoms in stellar remnant atmospheres. Picture the high-energy particles that continuously bombard all objects in space, now so degraded by cosmic expansion that they lack sufficient energy to strip electrons from atoms. Research by cosmic ray physicists shows that cosmic rays, like all radiation, lose energy as the universe expands, their wavelengths stretching and their energies diminishing. Currently, cosmic rays range from millions to billions of electron volts, but by 5.6 trillion years, even the highest energy cosmic rays will have been redshifted to energies below atomic ionization thresholds. The universe will have become chemically quieter, with atoms retaining their electrons without disturbance from radiation. This represents another way the cosmos is winding down, losing not just visible light, but the high-energy processes that alter matter. This reminds us that eventually even the most energetic phenomena will fade, leaving matter in its lowest, most stable states. In 5.7 trillion years, gravitational potential energy in the remaining bound systems will exceed kinetic energy by factors of millions to 1. Picture the few stellar remnants still orbiting supermassive black holes, now moving so slowly that their orbital velocity is negligible compared to the gravitational binding energy holding them in orbit. Virile theorem calculations show that gravitational systems normally maintain a balance between kinetic and potential energy, but as systems lose energy through gravitational wave radiation and other mechanisms, objects sink into deeper potential wells while moving more slowly. By 5.7 trillion years, the remaining bound objects will barely move, trapped in deep gravitational wells around black holes, their orbits taking millions of years to complete. These systems will have become nearly static, frozen in gravitational molasses, moving but so slowly that change becomes imperceptible. To think that motion will have nearly ceased even in gravitationally bound systems, that orbits will span timescales comparable to the age of our current universe. In 5.8 trillion years, the primordial helium created in the Big Bang will remain virtually unchanged, while heavier elements continue slow radioactive decay. Imagine helium atoms that formed 3 minutes after the Big Bang, now 5.8 trillion years old, chemically and physically identical to when they were created. Research by nuclear physicists confirms that helium-4 is completely stable with no known decay modes, making it effectively eternal. Meanwhile, trace amounts of naturally occurring radioactive isotopes will have continued their decay, with isotopes like uranium-238 and thorium-232 depleted to unmeasurable levels. A white dwarf containing primordial helium will find that material completely unchanged, while other elements have slowly transmuted through radioactive decay. The universe will retain a perfect memory of its first minutes in the form of helium that never changes. In a sense, helium atoms are time capsules from the universe's birth, eternal witnesses that will outlast stars, galaxies, and perhaps even protons themselves. In 5.9 trillion years, angular momentum conservation will have caused any accreting black holes to spin up to near maximum rotation rates. Imagine a supermassive black hole that has consumed thousands of stellar remnants over trillions of years, each adding not just mass but angular momentum, causing the black hole to spin faster with each merger. Research by Bardin Press and Tucholsky established that black holes can spin at up to 99.9% of their theoretical maximum, where the event horizon nearly touches the ergosphere. As a black hole accretes material, it gains angular momentum preferentially because, in falling matter, carries orbital angular momentum. By 5.9 trillion years, black holes that have undergone significant accretion will have spun up to near maximal rates, rotating at significant fractions of light speed at their event horizons. These spinning black holes will have stored enormous rotational energy in the twisted space-time around them. This reminds us that black holes are not static objects, but dynamic systems that evolve, gaining not just mass but rotation as they consume their in 6 trillion years. The separation between the cosmic event horizon and any given observer will have increased to encompass regions containing trillions of former galaxies. Picture an observer on a stellar remnant, surrounded by a spherical boundary beyond which no light can ever reach them. A horizon that now encompasses a volume containing the scattered remains of what were once trillions of galaxies. Calculations by Krauss and Scherer show that in an accelerating universe, a cosmic event horizon forms at a finite distance, beyond which objects recede faster than light can travel. As dark energy continues to drive acceleration, this horizon moves outward, but the observable universe paradoxically contains less and less as objects cross the horizon and disappear. By 6 trillion years, an observer would find themselves in an island universe, isolated from all but the nearest remnants. The rest of the cosmos will have receded beyond any possibility of contact or observation. To think that the universe fragments into causally disconnected regions, each observer trapped in their own cosmic bubble, forever isolated from the rest of reality. In 7 trillion years, the probability of any two stellar remnants passing within 1 light year of each other will have dropped below 1 event per trillion. Cubic light years per trillion years. Imagine a region of space encompassing 1 trillion cubic light years, and over the entire span of 1 trillion years, perhaps just one close encounter between stellar remnants occurs within that entire volume. Research on stellar dynamics shows that encounter rates depend on number density and velocity dispersion, both of which decrease as objects disperse and cool. By 7 trillion years, the universe will be so empty that close encounters between objects become fantastically rare. Statistical flukes in a cosmos of isolation. An observer stationed at one stellar remnant would wait quadrillions of years, on average, before witnessing another remnant. pass within observable distance. The universe will have become a place where proximity is rarer than the most exotic particle interactions in our current universe. This reminds us that as expansion continues, the cosmos transforms from a place of frequent interactions to one where objects exist in nearly perfect isolation, events becoming vanishingly rare. In 8 trillion years, quantum decoherence timescales for macroscopic objects will exceed the age of the universe itself due to environmental isolation. Picture a black dwarf floating in complete isolation. Its quantum state, theoretically capable of maintaining coherence for timescales longer than the universe has existed, simply because there is nothing left to interact with it and collapse its wave function. Research by Zurek on quantum decoherence shows that macroscopic objects lose quantum coherence through interactions with their environment, but in the extreme isolation of 8 trillion years hence, environmental interaction rates approach zero. A stellar remnant separated from all other matter by billions of light years will experience decoherence so slowly that quantum effects could theoretically persist at macroscopic scales. The universe will have become so empty that the boundary between quantum and classical behavior blurs even for planet-sized objects. To think that isolation itself could allow macroscopic quantum superpositions to persist, that loneliness might permit stellar remnants to exist in quantum states normally reserved for individual atoms. In 9 trillion years, supermassive black holes will have accreted effectively all matter that remains gravitationally bound within their influence spheres. Imagine a black hole that once anchored a galaxy, now containing perhaps 15 billion solar masses, having slowly consumed every stellar remnant that remained in orbit around it over the preceding trillions of years. Calculations by Kip Thorne and Roger Blandford show that objects lose orbital energy through gravitational wave emission at rates dependent on their mass and orbital separation, eventually spiraling into the central black hole. By 9 trillion years, this process will have run nearly to completion, with perhaps only a handful of the most distantly orbiting objects remaining. These black holes will sit in otherwise completely empty space, having swept their surroundings clean of all matter. The gravitational feeding process that began with galaxy formation will have reached its conclusion, with black holes having gathered and concentrated all nearby mass. In a sense, black holes represent the universe's ultimate destiny for structured matter, the final resting place where gravity completes its patient work of collection and concentration. In 10 trillion years, the cosmic microwave background will have redshifted to wavelengths exceeding the size of galaxy clusters and temperatures below 1/billionth of a Kelvin. Imagine the ancient light from the Big Bang, once visible as microwave radiation, now stretched to radio waves with wavelengths spanning millions of light years and energies so low they are barely distinguishable from the quantum vacuum itself. Research from NASA's COBE and Planck missions established the CMB's current temperature at 2.725 Kelvin, but continuous cosmic expansion stretches these photons relentlessly. By 10 trillion years, the CMB will have cooled to approximately 0.00003 Kelvin, with individual photons carrying almost no energy whatsoever. Any civilization existing at this epoch would find the CMB completely undetectable with any conceivable technology, its photons indistinguishable from quantum noise. The universe's baby picture. The radiation that has traveled since the cosmos was 380,000 years old will have faded into practical non-existence. This reminds us that even the most ancient and pervasive radiation in the universe is temporary, eventually stretched by expansion into a whisper so faint that it merges with nothingness itself. erasing the final visible evidence of the universe's fiery birth.